Okay, it is 6 o'clock, so let's get started. Welcome to the Silicon Valley chapter of IEEE Computer Society. I'm the chapter chair, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE, with more than 4,000 subscribers in our mailing list, more than 1,400 paid members, and a strong following of over 12,300 on Twitter alone. We are uniquely positioned by the virtue of our location, and we are really very fortunate to have distinguished speakers like today's speaker, Professor Carrera, who will be talking on nature-inspired optimization algorithms applied to control systems. During the design of control systems, the adjustment of controller parameters plays a fundamental role in the performance of the transient and steady-state regimes. From this perspective, the tuning of controller parameters has been performed using various methods and tools. But recently, meta-heuristic algorithms have improved tuning procedures to ensure the operation and stability of those systems. Thus, optimization algorithms that mimic the evolution of self-organizing biological systems, also called nature-inspired algorithms, have gained great relevance due to their significant potential for solving optimization problems. In particular, this talk presents the basics of several nature-inspired optimization algorithms and their application to tune the parameters of the fuzzy logic controller of a nonlinear magnetic levitation system, and also an energy management system for a residential microgrid. Various results are provided to highlight and compare the features of the optimized controllers. Today's speaker, Professor Enrique V. Carrera, received his bachelor's degree in electronic engineering from the Armed Forces University, Ecuador, in 1992, and his master's degree in electrical engineering from the Pontifical Catholic University of Rio de Janeiro, Brazil, in 1996. In 1999, he received his doctorate in computer engineering from the Federal University of Rio de Janeiro, Brazil. He was a visiting scholar at the University of Rochester, USA in 1999. From 2000 to 2004, he was a postdoctoral associate in the Department of Computer Science at Rutgers University, USA. Since 2011, he has been a professor at the Armed Forces University, Ecuador. He has also collaborated as an external professor at King Juan Carlos University, Spain, since 2014. Currently, he is an IEEE senior member and has an appointment as a distinguished visitor to the IEEE Computer Society. His main research areas include signal processing and computational intelligence. So before I turn it over to Professor Carrera, just wanted to remind you that the links to video and slides will be posted on our website in about a week. The video will be made available on IEEE TV, and it is currently being broadcasted live on YouTube. So please feel free to post your questions on the chat window or in the chat window of the Zoom session or on the chat window of the YouTube live broadcast. So with that, I turn it over to Professor Carrera. Professor Carrera, it's all yours.
Thank you. Good evening, everyone. Thank you for being here. I would also like to thank Professor Vishnu Pendyala and the IEEE Silicon Valley's Computer Science chapter for the kind invitation to this webinar. It's my pleasure to give you this talk on how nature-inspired optimization algorithms can be applied to control systems. This work has been developed at the Armed Forces University in Ecuador within the PROCONET group led by Professor Diego Arcos, which belongs to the Department of Electrical and Electronics Engineering. Let's see the outline that I have prepared for this talk. First, I'm going to give you a brief introduction to the topic of this talk. After that, I'll introduce the basics of fuzzy logic controllers Next, I describe the most important nature-inspired optimization algorithms that have been used in our work. Then I'll present two application examples, including a basic control system and also a more sophisticated example based on residential microgrids. Finally, some important conclusions and future works will be detailed. Let's see an overview of the work that I'm going to discuss in this talk. As many of you probably already know, today control systems are an essential part of any industry or automation project. A control system is basically a set of devices that regulates or manages other devices or systems through control loops. The figure here below shows a simple view of a control system where a certain process is controlled by means of a feedback loop. Currently, most control systems are computerized using, for that, sensors, microcontrollers, programmable logic controllers, smart or intelligent electronic devices, among other alternatives. In this way, current control systems are used to enhance the production, efficiency, and safety in many areas. In other words, control systems are essential to humanity these days. So, a typical problem that we have with these control systems is that even simple systems have some parameters that must be adjusted to achieve the desired performance of the controlled processes. Thankfully, there are some established methods for setting these parameters in several types of control systems. However, modern control systems, such as fuzzy logic controllers, can have tens or even hundreds of parameters that need to be optimized. Therefore, finding the optimal set of parameters to achieve the desired performance is a very difficult task in these modern controllers. Generally, the optimization of this type of controllers has been carried out through some heuristic procedures with acceptable results, but also high cost, as we'll see along this talk. Fortunately for us, several nature-inspired algorithms have been proposed to solve optimization problems in a wide range of applications. Some examples of such techniques are genetic algorithms, differential evolution, firefly algorithm, particle swarm optimization, BAT algorithm, and colony optimization, Cuckoo Search, and so on. Some applications where these algorithms have been applied successfully are image processing, job scheduling, chemical processes, operation and control of electric power systems, vehicle routing, control of autonomous vehicles, mobile networking, multi-objective optimization, among others. So the selection of the controller parameters can be seen as an optimization problem that could be formulated in terms of a cost or objective function. This talk is exactly about the methodology that we can use to adjust the parameters of the fuzzy logic controllers through several nature-inspired optimization algorithms. Specifically, we are going to optimize the controller parameters of a magnetic levitation system and a microgrid energy management system. The magnetic levitator system here in the figure is a very simple system, usually used for academic purposes. The basic system is made up of electromagnets that allows ferromagnetic objects to remain in the air, as shown here. Note that the system also has some sensors to determine the distance of the object to the coil. In this case, the ferromagnetic object is a simple iron ball. On the other side, we also have a residential microgrid system. This is a more complex system to control. As we can see in the figure, several hybrid renewable energy sources, fossil fuel generators and batteries are connected to the domestic load and also exchange energy with the main power grid. The energy management system of this residential microgrid here in the center aims to minimize power peaks and fluctuations on the power profile exchanged with a utility network. This is, as I said, more sophisticated and realistic process to control, so the challenges are greater. After this brief overview, let's turn our attention to what a fuzzy logic controller is. In contrast to classical control theory that has been successful in controlling well-defined systems, many engineering problems require more sophisticated control techniques. This is because of the presence of strong nonlinearities, changing environments with uncertainties, or systems that are difficult to model. Therefore, the fuzzy logic controller technique provides a formal methodology for representing, manipulating, computing, and incorporating human intelligence directly into automatic control systems. It has shown that fuzzy logic controllers offer potential advantages over conventional control schemes. Basically, less dependency on quantitative models, decision-making in natural language, learning capability, greater degree of autonomy, easier and cheaper implementations, friendly user interface, among the most important advantages. In fact, by using this linguistic approach provided by the fuzzy theory, human knowledge about the system to be controlled can be integrated into the control theory. Fuzzy logic controllers can cover a wider range of operating conditions and can be applied from a simple home heating controller to even large industrial control systems. This figure, here at the bottom of the slide, shows that the fuzzy logic controller occupies the same place as any other controller within the control loop. And we can see that these controllers have three main stages or subprocesses, in addition to a rule database. The three main subprocesses are falsification, the inference mechanism that use the rule database, and the diffusification process. Here we have a more detailed figure of a fuzzy logic controller, and we can see its three stages or subprocesses. The basic idea of the fusification stage is to transform the numerical values of the input variables into linguistic concepts using membership functions. Next, the linguistic variables here and the rule database are used to implement a linguistic control strategy based on the if-then inference mechanism. Since several rules can be activated for a particular set of inputs, the output of the inference mechanism is the union or intersection of several linguistic values that need a diffusification process to obtain a crisp numerical value that actually controls the system. If we use the union of the linguistic values, the inference mechanism is called Mandami-based inference. Now we are going to continue analyzing these three stages of the fuzzy logic controller in a more detailed way. First, as I already mentioned, the falsification process transforms the input variables in numerical format into linguistic variables. For that, we use membership functions like the ones shown in the figure. Traditionally, the shape of these membership functions is like a triangle, and its number varies between 4 and 9 linguistic concepts to cover all the continuous range of the input variable. Here in this example, we have 5 linguistic concepts for covering between minus 16,000 and plus 16,000, namely big negative, small negative, 0, small positive, and big positive. This means that, for instance, a value of 4,000, around here approximately, has a probability of 0.5 of being considered 0, the yellow triangle, and also a probability of 0.5 of being a small positive number, the purple triangle. Obviously, from the point of view of the defined fuzzy linguistic concepts. Moreover, the inference mechanism approximates the human reasoning to assign outputs according to the linguistic information. Let's see the next figure to understand this mechanism. This is a very simple example of the inference mechanism. Basically, we have two rules here in the bottom that are triggered depending on the input variables x and y. The output is the variable z. The particular values of x and y intersect the membership functions associated with linguistic values a1 and a2 in the case of x, and v1 and v2 in the case of y. The two rules imply that the linguistic values their outputs are c1 and c2 for rule 1 and rule 2 respectively. As the figure shows, the c1 and c2 linguistic concepts are added to the output using the minimum membership of their corresponding outputs. The final fuzzy set is the combined conclusion of the two rules, and it is presented on the right side of the slide. Once we have the final fuzzy set, the diffusification process converts the fuzzy output to a numerical value required to control the system. In this particular example, we are using the center of gravity method to generate a single numerical value. It's important to mention here that there are several variations of these three stages. The membership functions, for instance, can vary in number, shape, and distribution. The inference mechanisms can use approaches that are different at the minimum intersection, shown in the previous example. And the diffusification method can use other alternatives to summarize the fuzzy set into a crisp numerical value. In conclusion, the main parameters to optimize in a fuzzy logic controller, in addition to the number, position, and shape of the membership functions, are the rule database and the various computing mechanisms. Now that we understand what is a fuzzy logic controller, let's focus on the details of the nature-inspired optimization algorithms. Even with the ever-increasing power of modern computers, it's still impractical and undesirable to use simple brute force approaches to optimize many real-world applications. Today, the nature-inspired algorithms tend to be global optimizers, using a swarm of multiple interacting agents to generate search movements in the search space. Such global optimizers are typically simple, flexible, and yet surprisingly efficient. However, these meta-heuristics don't guarantee that the optimal solution will always be found, but they do guarantee that a good enough solution will be found. We have selected only a few featured algorithms to study the optimization of control systems, and these algorithms are described in the following slides. To start, the genetic algorithm is a model of the biological evolution based on the theory of natural selection. In order to understand this proposal, it is necessary to focus on its three main activities required by the algorithm. First, the solutions are represented through high-dimensional vectors. So we need to define the coding of our candidate solutions as a vector. The possible solutions are modified by mutation and crossover operator. So we need to establish those operators for our vectors. And finally, the solutions are selected through the fitness assigned to each of them. So we must choose a fitness function that indicates how good is a particular candidate solution. Note that the genetic operators crossover and mutation form an essential part of the genetic algorithm as a problem-solving strategy. It has also been proved that there are many advantages of the genetic algorithms over traditional optimization techniques. For instance, the ability to deal with complex problems and their innate parallelism. This figure summarizes the continuous processing of a genetic algorithm. We start by creating a random set of possible solutions to the problem to be optimized. Note that this is codified as multidimensional vectors. We select the best solutions specimens based on the fitness function, a kind of inverse cost function. Then we apply the crossover operator, which typically generates two new solutions based on the characteristics of two selected specimens. The selection of the specimens for crossover could be completely random or based on the roulette wheel method. That method we'll discuss in the next slide. After that, we apply the mutation operator, which generates random variations in the representations of the solutions. In fact, the mutation operator is normally limited to a fixed percentage of operation at each generation. And finally, we select again the best specimens and continue these iterations until we find a good enough solution to the problem that we are optimizing. Let's understand this process with a simple and concrete example. Imagine that we need to find the maximum of a two-dimensional function g of x and y using genetic algorithms. First, the representation of the solution could be a two-dimensional vector, x sub I, with I between 1 and capital N, where capital N is the size of the population. The crossover operator could take two vectors, xi and xj, and mix the elements of these two vectors like the examples, xi with yj and xj with yi. The mutation operator would simply add some small random numbers, epsilon, to each element of the vector x sub I. Since we are finding the maximum of a function, the selection of the solution could use the value of that function at that point, x sub I, plus the roulette wheel. The roulette wheel method allows us to select any candidate solution, giving preference to the solutions with highest fitness values, the green one or the blue one. But we can see that from the figure that even low fitness solutions can eventually be selected, like the purple one. Now, let's talk about differential evolution. Like genetic algorithms, differential evolution is a method that optimizes a problem by interactively trying to improve a candidate solution with regards to a determined measure of quality. Differential evolution is used for multidimensional real-valued functions, that is numerical optimization, but doesn't use the gradient of the problem being optimized. In fact, differential evolution doesn't require that the optimization problem can be differentiable. Differential evolution can also be used for the optimization problems that are not even continuous, are noisy, or change over time. Basically, differential evolution optimizes a problem by maintaining a population of candidate solutions and creating new solutions by combining the existing ones according to its simple formulas. Here are the formulas. A candidate solution randomly select a pseudo time t is interactively updated considering that vector x sub I at t plus 1 is equal to vector xi at pseudo time t plus delta of vector x sub I at t. The mutation operator, delta of xi at t, is calculated as lambda times vector xi, the xj, minus vector xk at pseudo time t, where xj and xk are two other randomly selected vectors. This mutation operator can have a specific mutation rates for each component of the vector, and vector xi at t plus 1 only replaces vector xi at t if the fitness of xi at t plus 1 is greater than the fitness of xi at pseudo time t. Some variations of differential evolution also use some kind of separate crossover operator, but we are not going to discuss this here since the simple operator that we have presented already makes basic mutation and crossover operators. This figure condenses the update procedure of vector xi. considering two other vectors, xj and xk. The difference between xj and xk is used as the mutation vector applied to xi and scaled by a lambda factor here. In summary, differential evolution is a very effective global search algorithm with a simple mathematical, or I should say numerical structure. Similar to the previous presented algorithms, particle swarm optimization is another nature-inspired algorithm. Is a stochastic and multi-agent parallel global search technique that develops global optimum solutions based on local candidate solutions. The main inspiration of the particle swarm optimization comes from the swarm movements of bird flocks and schools of fish. The potential solutions called particles move in the problem space following the current optimum particles. So the mutation operator considers not only the current positions of the particles, but also their velocity. Moreover, the movements of the particles are guided by their own best known positions in the search space, as well as by the best known position of the entire swarm. The position and velocity of particle I at any iteration of pseudo time t are interactively updated, like the previous algorithms, using vector xi at t plus 1 equals to vector of xi at t plus delta of vector xi at t. The velocity of particle v sub I at t plus 1 is equal to velocity v sub I at pseudo time t plus delta of v sub I at t, with delta of x sub I at pseudo time t equals to velocity v sub I at t plus 1. In addition, delta of velocity v sub I at pseudo time t is equal to alpha times epsilon 1 times the difference between the best known position and the current one x sub I at t plus beta times epsilon sub 2 times the difference between the best visited position but x sub I and the vector x sub I at pseudo time t. It's important to say that epsilon 1 and epsilon 2 are random numbers evenly distributed between 0 and 1. It has been demonstrated that particle swarm optimization is computationally efficient in terms of both speed and memory requirements. This figure summarizes the update of the current position of xi, considering its own velocity, the blue line, the best known position already reached by the swarm, the green circle, and the best position already visited by xi, the orange circle. As I said, in blue is the current velocity, and in red is the final velocity that takes the particle to its new position, according to the best known previous position, the green one and the orange one. This figure also attempts to illustrate the application of particle swarm optimization to find the minimum of a two-dimensional function. We can see the population of particles with their current velocities on the left and the values of the cost function from each position of the search space on the right. All the particles are moving and will tend to end up at the bottom of the cost function after the algorithm finishes. Next, let's talk about our last algorithm, the Cuckoo Search. The Cuckoo Search algorithm is a kind of newer alternative within the nature-inspired optimization algorithms. Cuckoo Search is based on the aggressive reproduction strategy of some cuckoo species and their interactions with the host species, such as warblers. The main assumptions of this model are basically three. Each cuckoo only lays one egg at a time and dump it in a randomly chosen nest. The best nest with high quality eggs will carry over the next generation. This is called elitism. And the number of the available host nests is fixed. The algorithm is also enhanced by the so-called Levy flights rather than by simple isotropic random walks. The X laid by cuckoos, that is the candidate solutions, can be discovered and abandoned with the probability P sub A, realized by a Heaviside step function H with the use of a random number epsilon that can have values between 0 and 1. Any solution at iteration t is updated using vector x sub I at t plus 1 is equal to vector x sub I at pseudo time t plus delta of vector xi at pseudo time t. And this delta of vector x sub I at pseudo time t is equal to alpha times vector s times the Heaviside step function of p sub I minus epsilon times the difference between vectors x sub j and x sub k at pseudo time t, where the step size s is drawn from a Levy distribution with an exponent lambda, and xj and xk are two other randomly selected vectors. In addition, the similarity of 2x, that is the similarity of two solutions, xj and xk, can be roughly measured by the difference xj minus xk. Note that the intensification and diversification search strategies are important elements of this algorithm. Basically, intensification focuses on the search in a local region where a good solution has been found, while diversification generates diverse solutions far enough from the good solutions to explore the search space on a global scale. In essence, Cuckoo Search has a strong mutation or crossover operators at both local and global scales. Recent studies show that Cuckoo Search is potentially more efficient than other algorithms, since the Cuckoo Search has well-balanced intensification and diversification search strategies. And the Cuckoo Search is also a robust, precise, and fast algorithm. As it was the case in previous algorithms, there are different variants of the Cuckoo Search algorithm that have been proposed in the recent years, but we are not going to delve into it by now. Here, we can see a figure that represents the search process of this optimization algorithm. As we can see, we have two types of search: local random walks like L1 and L2, and more global flights to distant nests. The worst solutions are abandoned, and each cuckoo only lays one egg at a time. To the end, the best nest, that is the global solution, is selected from the majority of the cuckoo birds. Just to give you some idea of other nature-inspired optimization algorithms, I list here three other well-known algorithms. The Farfly algorithm, for instance, is based on the attraction and flashing behavior of tropical fireflies. This algorithm is a little bit similar to differential evolution, since each position is updated according to the attractiveness of a random pair of fireflies. Similarly, the BAT algorithm is other alternative inspired on the echolocation of microbats and the associated frequency tuning characteristics. Its formulation is similar to particle swarm optimization, since it represents the position and velocity of solutions, but the velocity is updated as a function of the frequency range and loudness of the emitted sounds. Finally, the flower pollinization algorithm is based on the pollinization processes and characteristics of flowering plants, including biotic and abiotic pollinization, as well as flower constancy. Well, and now let's run through our application examples with two implementations of fuzzy logic controllers optimized by these nature-inspired algorithms. To start, the magnetic levitation system shown in the figure could be modeled through the following variables. Two inputs, the error position of the ferromagnetic sphere, that is the reference d sub 0 minus the distance d, and the derivative of that error. One output is the variation required in the coil's current In other words, the derivative of the current I here in the circuit. In this system, as I mentioned, we need to define a reference distance d sub 0, in which the ball must remain in such a way that the electromagnetic force compensates the weight of the ball. The proposed control system structure is shown here in this figure. Due to the nonlinear dynamics presented by the magnetic levitation system, a fuzzy logic controller is applied to keep the sphere at position d sub 0. This is a simple and robust nonlinear control system. In addition, the controller is easy to implement and is based on the linguistic description of the behavior of the global system. Note that through the set point block, we define d sub 0, and subtracting the actual distance d, the output of the system, we obtain the error. The error and its derivative are fed to the fuzzy logic controller that defines the variation in the coil's current here. That parameter is then applied to the magnetic levitation system to keep the ball close to the set point. This basic fuzzy logic controller uses symmetric and uniform distributed membership functions, considering 5 linguistic levels: big negative, small negative, 0, small positive, and big positive, as in a previous slide. Therefore, the rule database includes these following 25 rules. For instance, here, if the error is practically 0, and the derivative of that error is very negative, then the coil's current is varied by a small positive amount. The proposed fuzzy logic controller also assumes a Mandani-based inference and a center of gravity diffusification method. In addition to this basic proposal, the Cuckoo Search algorithm was applied to optimize the position of the membership functions and the rule database. The objective or cost function takes into account the real position error, the settling time of the step response, and the maximum percentage of overshoot. We compared the step response of the magnetic levitation system using a classical state space controller, the basic fuzzy logic controller, that is without any optimization, the fuzzy logic controller with optimal membership functions, and the fuzzy logic controller with optimal membership functions and rule database. We have 33 variables to optimize for the membership function and 25 variables for the rule database. And we use a fixed population size of 25 nests. Here we can see the comparison of the 4 systems that we have mentioned. Each line is the step response of every evaluated system, specifically the response of the system to an instantaneous change in the reference instance, the d sub 0 variable, by 8 millimeters. We can see that the system that is not optimized, the purple line, cannot reach the desired set point. The other 3 systems do a good job, but let's see, assume in this part of the figure that is most interesting. Here we have the classical state space controller in green. Here is a very nice response, the green one. The fuzzy logic controller with optimal membership functions in orange is very similar to the state space controller. And the fuzzy logic controller with optimal membership functions and rule database, the blue line. We see that the traditional state space controller makes a good job, but the rise time, that is the value here, these arrows, see the rise time is about 0.39 for the case of the state space controller, but for the optimized controller is approximately 0.19. So the rise time is better for the fuzzy logic controller optimized by our proposal. We see, as I said, that the rise time of the completely optimized controller is faster. In addition, the matrix of settling time and overshoot percentage are fulfilled in all these variations. The overshoot are these metrics here, percentage of overshoot, 5% approximately in all the cases. And the settling time here is almost very similar, almost 0.5 seconds. In this way, the proposed approach has successfully achieved the optimization goals, such as settling time, overshoot, and steady-state vertical position. For that, the membership functions have been redefined, as shown in the figure presented here, for the position error membership functions. Note that the change in the position of these triangular functions. In red are the original positions, and in blue are the new optimized positions. The rule database has also been updated. In fact, 15 rules, the ones that are in blue, have been redefined by the optimization algorithm. And to finish the discussion of on the magnetic levitation system, this table summarizes the cost function of each type of controller. Remember that the cost function depends on the position error, the settling time, and the maximum percentage of overshoot. Note that the cost associated to the fuzzy logic controller that optimize the membership functions here and the rule database is an order of magnitude better than the other two controllers, 0.5 versus almost 5,000. So it's an order of magnitude better, our proposal. Now, let's analyze a more complex fuzzy logic controller, an energy management system for a residential grid-connected microgrid. The objectives pursued by an energy management system are usually economic, related to minimize the operating cost or maximize its income. However, due to new regulations from the network operators, current objectives include to minimize power peaks and fluctuations in the power profile exchange with the utility network, that is the electrical power grid. Therefore, the fuzzy-based energy management strategy for the studied residential microgrid considers the energy state forecasting, peak shaving, and demand management. As mentioned before, the main benefits of fuzzy logic controllers are that qualitative knowledge of the desired system behavior can be included as if-then linguistic rules, especially for the control of dynamical systems where an analytical model is not available or is too complex due to, for instance, the presence of nonlinear terms. Here, the fuzzy logic controller is the best alternative. However, the design of the fuzzy logic controller involved in this energy management system requires the selection of several parameters, such as the type and number of the membership functions, the rule database, and the variation range of each variable. The following evaluation is performed considering real recorded and predicted data of renewable energy source electricity production and load demand during 1 year. The electrothermal microgrid architecture considered in this work is shown in this figure. We can see that the simulated microgrid includes a photovoltaic heat generator, a wind turbine, and batteries that power a domestic load. In addition, we also have a domestic hot water system in the red box that uses solar thermal collectors and electric water heater for supply the domestic hot water consumption. And finally, the entire microgrid is connected to the utility network in case that the load needs additional power from the grid. This figure represents the domestic load demands in kilowatts considered for the year that the simulation lasts. These are real data from a typical European household. See that during winter and summer, the load demand increases significantly, especially during summer, these months here and here. In this way, the fuzzy logic controller of the energy management system has two inputs, one output and 25 rules that have been experimentally developed and validated. The input of the fuzzy logic controller are the current battery state of charge and the power forecast error for the previous 3 hours. The single output of the fuzzy logic controller is used to smooth the grid power profile. This fuzzy logic controller uses symmetric and uniform distributed membership functions, considering 5 linguistic levels for the inputs and 9 linguistic levels for the output. The total number of variables to optimize is 72, 25 rules, and 47 other parameters. The fuzzy logic controller also assumes a Mandani-based inference and a center of gravity diffusification method. The overall cost function includes all the criteria used to assess the quality of the grid power profile. Numerical simulation on the specific microgrid example are presented to compare the performance of 3 nature-inspired optimization algorithms, namely particle swarm optimization, differential evolution, and Cuckoo Search. In addition, we benchmark the performance of an energy management system based on the same fuzzy logic controller, but adjusted offline using a trial and error methodology. In terms of computing time, the particle swarm optimization algorithm is faster than the Cuckoo Search and the differential evolution, but the Cuckoo Search algorithm offers some advantages related to the reduction of power fluctuations and peaks in the grid power profile. Here we have the comparison of 3 nature-inspired optimization algorithms. Note that the y-axis is the fitness value and the x-axis the number of iterations. As I mentioned, in terms of computing time, the particle swarm optimization algorithm in blue is faster than Cuckoo Search and in green and differential evolution in red. But the Cuckoo Search and differential evolution algorithms have lower cost. Note here, almost 7.7 in both cases, and here we have 7.8. In fact, the Cuckoo Search offers some advantages related to the reduction of power fluctuation and peaks in the grid power profile. This last table just presents the final cost associated to each evaluated system. We can see the nature-inspired optimized systems, the 3 in the bottom, have a cost function reduction of around 13% with relation to the no-optimized system. In fact, the results demonstrate that the nature-inspired optimization algorithms obtain an acceptable response in relation to the main objective pursued by the energy management system. Since we have evaluated a simple and also a more complex control system with successful results, we hope that this methodology that we have presented here can be applied to many other systems. Finally, let me show you the main conclusions of this work and some future works that we have already started. We have presented a procedure to optimize the parameters of a fuzzy logic controller using nature-inspired algorithms. The main advantage of this approach is that little or no expertise is needed for tuning the fuzzy logic controller parameters. Numerical simulations have made it possible to compare the performance of several nature-inspired optimization algorithms. The obtained results highlight that the proposed algorithms can be applied to any system where the fuzzy logic controller technique is used in order to optimize an objective function that involves several system parameters. The different nature-inspired optimization algorithms present similar results as demonstrated in our evaluations. Moreover, the convergence time is a critical parameter that should be considered in any deployment, especially if a real-time implementation is required The set of input parameters that each algorithm needs must be understood to provide stability and robustness to the optimization task. Future work will focus on the design of a real-time adaptive fuzzy-based energy management system. The new design will update the fuzzy logic controller parameters at the same time as forecast variables, which could improve the efficiency of the energy management system. We are also looking for a simple method to adjust the variables of the nature-inspired optimization algorithms. And finally, we also want to evaluate new type of control systems where these nature-inspired optimization algorithms can be employed. Here, I have a list of some reference where you can find more information about the theory and examples discussed throughout this talk. As I mentioned, these works correspond to projects that are being developed in the PROCONNECT group at the Armed Forces University in Ecuador. That's all that I have prepared for this talk. I don't know if you have some questions that I can answer at this point, or please feel free to email me to this address. Otherwise, it would be my pleasure to answer any question or comment from you. And also want to end by thanking all of you for your attention to this talk, and again to Professor Pendyala for this cordial invitation. Thank you very much.
Thank you, Professor Carrera. It was really insightful talk. So we have one question on the YouTube live broadcast, live chat. So Ruben Lewis is asking, is there a reason you didn't use then genetic algorithm for either of these examples? I think you used, right?
Yeah, I don't use in the actual evaluation that we have made genetic algorithms, but I wanted to present genetic algorithms because it's the basics of all the other algorithms. As I mentioned, genetic algorithms is an older proposal, and all these new nature-inspired algorithms are based on this mutation and crossover operator and the way that the solutions are selected and how the solutions are codified. So I presented genetic algorithms as a motivation for the other three nature-inspired algorithms that I have used in the evaluations of the two examples that we use in our works.
Okay, one of the reasons genetic algorithms are not normally used is because they cannot scale well, right? So do you still think they're applicable to control systems, which are typically require a lot of scale?
It's more slow to the other algorithms because the other algorithms are applied to numerical optimizations. Genetic algorithms is a proposal that can be used not only in numerical problems, but also in symbolic ones. So the other three algorithms that are based in these ideas proposed by genetic algorithms are more oriented to numerical optimization. And because are oriented to this kind of application, are more faster than the basic genetic algorithms proposed a long time ago. Okay,
and how about deep learning frameworks? I mean, did you consider artificial neural networks for these optimizations?
No, we don't use these other frameworks like deep learning of artificial neural networks, but we can try to apply these new optimizations, these new frameworks could be a complement to the proposal that we have made until now. So we see that these nature-inspired optimization algorithms are very fast, and we don't need a kind of training that the other alternatives must need.
Okay, thanks. And so Greg is asking on YouTube channel, can you explain how the rule base was optimized in the first example? How were the rules parameterized?
Sure. The rule base is basically a table like this one. So trying to use basic knowledge about the problem, you can set up all these possible alternatives, knowing the error position and the derivative of the error. You define what is the variation in the coil's current. But normally there are too many options here that you can put. So we use the optimization algorithms, these nature-inspired algorithms, to be select the new options that maybe improve the result of the system. And the result is that in this case, some of these alternatives that we select previously using our intuition were improved, were changed to optimize the cost function. In this case, these 15 rules in blue have been changed if we compare with this original table here. So we see that some of these values are kept the same, but other ones are changed according to the need to improve the settling time of the overshoot percentage of some other value of the cost function.
Okay, thank you. So I had a question, maybe this is a very naive question, but fuzzy logic is approximate logic, right? And
Yeah.
the rules are deterministic. So what is the idea behind converting fuzzy logic inputs into deterministic if-then-else rules?
I don't know if I understand exactly what your question is, but note that the rules are deterministic, as in this example. If X is, for instance, if the error is low and the derivative of the error is high, then the output, the variation of the current should be a small positive. This is a deterministic rule, but note that this concept of small, almost zero, or big variation are concepts that we are not able to define in an easy way. So we have actually the real value of the error. And using this membership function, we convert a real value in a deterministic concept. In this case, A1 could be small, big, zero, etc. So using this conversion, we can apply these rules that are normally in our intuition about how the system works. But using these rules, also you conclude some language concepts that you should convert again to a numerical value, because the variation of the current couldn't you say just a small variation. You should say a real number. So after you convert all these concepts, the nominal concepts, into real value, this is the value that you should apply numerical value to the system that you are controlling. So actually, the rules are deterministic, but these rules are also improved by the nature-inspired optimization algorithms, because we are changing these rules. Here in the table that I showed before, we are changing the rules, because this table says when the error position is zero and when the derivative of the error is zero, keep the variation of the current as zero. So it's a deterministic, but we can change that rules because we are not sure what is the optimal rule that we should include in the system.
So depending on the fuzzy membership function, these rules apply, is it?
Yeah, because if you change the number of membership functions, of the position of the membership functions, you change the conversion of a real value to a conceptual meaning of a certain term, like a big negative or a small negative of zero. So changing the rules, the number of rules, the position of the rules, and the range that the rules cover in the input variable change everything about the behavior of the controller. That's because it's so important to optimize all these parameters. And there are many parameters, and it's very difficult by hand trying to resolve this optimization.
And how do we model the membership function?
How,
is it a mathematical function? Sorry.
Excuse me, I didn't understand what you said at the end.
How do you model the fuzzy membership function? Is it a mathematical function, or is it subjective, something?
Well, the membership function, normally you use a symmetric and always with a triangular form, shape, but you can use whatever shape you want and the number of rules that you need. So it's a very difficult, as I said, when you start trying to model this controller, define these parameters. For instance, the membership function shouldn't be necessarily triangular. Could be a kind of rectangular or some other shape that the rule could have. And the number in this case are 5, but you can use 7, you can use 9 membership functions, and every value in the x-axis is be converted in a concept. In this case, for instance, if the position is 0.002 here, it's very, very probable that it's a small positive, but it's very probable that it's a 0 because the value convert a membership function that is a value between 0 and 1. So it's very probable that it's a 0 concept, and is a small probability that is a small positive number. And that conversion also depends on this configuration. And this configuration is very hard to define, as I said. It's better if you just leave the problem to the heuristic, in this case, the nature-inspired optimization algorithms, to define the number, the shape, the position of these rules.
Okay, thank you. So there's a comment on the YouTube live chat from Ruben Lewis. He's saying that the graph showing the updated parameters for the magnetic FLC was really helpful. It helped me understand what an optimization looked like once completed. So thank you for that, Professor Carrera. And Eugene Freeman has a question. He wants you to explain your definition of linguistic.
Well, the definition of linguistic is that normally the people try to define values using these terms like very negative, very positive, almost 0. But there is not a well-established convention that always 0.5 should be almost 0. In certain cases, 0.5 could be a very high number depending on what is the variable that you are measuring. So because there is not a convention, we should establish this transformation of a real number into a linguistic concept. For instance, in the kind of the position error, if the position error is in centimeters or in millimeters, the real value is different. But in some cases, different real values can be converted to the same linguistic concept. For instance, the error is almost 0. What means that it's almost 0? That the variation with the relation to the reference point is insignificant. This insignificant concept is a linguistic concept and should be interpreted by the membership functions. The membership function defined through these triangular shapes what is insignificant, what is almost 0 in the case of the value that is the input of the system.
So linguistic essentially means, like, because they are like if-then-else rules, they are more language oriented. We are using a language, so that's why it's called linguistic, right?
Yeah, the rules are defined in this linguistic space. For instance, as I put in this example, you said, if the error is small and the derivative of the error is big, then the current should be, I can say, zero. You shouldn't change the current in this position, but you should define in this linguistic space what are the conditions that you consider to define the output of the rule.
Okay. Yeah, I think that we are caught up with the questions on the YouTube chat. And on Zoom chat, there is a question. Are you willing to share a file video meeting and slide documents with me? So as I mentioned, the video will be shared on IEEE.tv, and it'll be the link will be provided on our website. And it's also broadcast live, so it's on the YouTube channel. So if you have enrolled, registered with Eventbrite, you should be able to get to the video and the slides about a week after the talk, after today. And the other thing is, so this is from Soravit Promrak. I think he is attending from Thailand. So do you have a certificate training CPD or CPE? Because the certificate affects the position, the salary base, and the education for me. So this is just a 1 hour talk, so I don't think we can provide certificates to the attendees, but we do provide certificate to the speaker, which is what I'll bring up now. So we really thank, oh, I need to share my screen once. So Professor Carrera, I will start sharing my screen.
Sure.
Thanks. So this is our appreciation, Professor Carrera, for your kindness for coming and enlightening us on an important topic. I'll also email this to you. Unfortunately, it's not an in-presence meeting, so we cannot present you with a plaque, physical plaque, but a small token of our appreciation. And a little bit about our event. So today's talk is this, and next month we are having a Ask Me Anything session on artificial emotional intelligence, deep learning, AI, and other stuff by Professor Bjorn Schuller. He is a professor in Imperial College London. So this will be held on the 22nd of March at noon Pacific time. And again, this is also a free event, so please everyone take advantage of this. And of course, send me your questions in advance so that I can forward them to Professor Schuller, and you'll have a chance to ask follow-up questions during the session. So that's event for March. And on 12th of April, we are having Cisco Senior Technical Operations Leader and McGraw-Hill book author, Dr. Ramachandra Gambhir. He will be presenting on sustainability. It's a very important topic. So design for sustainability, green hardware, software, and network. So the current plan is to have this in person, but we are not sure. We will announce it on Eventbrite, whether this is in person or on Zoom. And then we are always looking for volunteers. We started a new magazine, the flagship publication of Silicon Valley chapter, Feed Forward. So we are looking for editorial support and good articles if we have any. Then we are looking for volunteers for social media, handling our social media pages, groups, and publicity. Student chapter and school liaison. And we are also planning to organize a conference. So we are looking for help with that, member recruitment, and any other ways you can contribute, please email us. So with that, I once again thank Professor Carrera from the deep of my heart, from the chapters on behalf of the chapter. Thank you again for spending the late evening with us. I know it's almost past 10 o'clock. Really appreciate your dedication to the profession. Thank you.
Thank you, Professor Pendyala. I also want to thank you to everyone connected to this webinar. Thank you very much.
Yeah, sure.
Thank you.
Good night, everyone.
Good night.
Thank you from the professor.
Yeah, thank you.
Thank you, Professor Pendyala. It's a pleasure to talk in your chapter. See you.
Oh, it was, yeah, we'll hopefully keep in touch and then hope to see you sometime in future as well.
Sure.